Hi everyone! This video is about the Stern-Gerlach experiment. In this experiment, silver is heated so much in a furnace that it becomes gaseous. A few individual silver atoms leave the furnace through a small epetscher in the direction of an inhomojeneous magnetic field. Behind the magnetic field there is a photoplate which the silver atoms hit and leave an imprint. The result is that the silver atoms are deflected either up or down. Some of you might now think that the distraction is due to the Lorentz force. However, these are not positively or negatively charged particles that fly through the magnetic field. They are complete silver atoms with an equal number of protons and electrons. Therefore, no resulting Lorentz force acts on the silver atoms. Let's take a closer look at the silver atoms. A silver atom has 47 electrons. The electrons are at different energy levels. It is already noticeable that there is an even number of electrons at every energy level. Only one is at the highest energy level. Let's take a closer look at the electrons. The Pauli principle states that no two electrons on a shell may have completely the same quantum numbers. The main quantum number indicates the shell on which the electron is located. In simple terms, the distance between the electron and the atomic nucleus. Let's start with the two electrons on the K shell. The secondary quantum number, S,P,d/f, indicates the shape of the orbital in which an electron is located with a probability of 90%. The magnetic quantum number, M, indicates the orientation of the orbital shape. At first glance, one might think that the two electrons on the K shell are the same in all quantum numbers. But according to the Pauli principle, they are not allowed to do that. However, if we take a closer look at the two electrons, we notice a difference. The final missing quantum number of an electron, the spin, is what differentiates these two electrons. The left electron has a spin down and the right electron has a spin up. These two electrons, which have completely identical quantum numbers except for the spin, are called paired electrons. If you look at the electrons on the other shells, you can see that they consist entirely of paired electrons. Only on the highest shell there is a single unpaired electron. This electron can assume both spin states, spin down or spin up, without breaking the Pauli principle. Now let's go back to our experiment. As already mentioned, whole silver atoms always fly through the magnetic field. Now let's look at what happens to all 46 paired electrons as they fly through the magnetic field. The spins of the two electrons must be opposite at all times. Otherwise, they would break the Pauli principle. Before entering the magnetic field, the spins are oriented in all possible directions. When entering the magnetic field, the spins align with the magnetic field. In this case, the spin of the left electron points in the same direction as the magnetic field, and the spin of the right electron points in the opposite direction. An atom that consists only of paired electrons is not deflected in the magnetic field. But the silver atom has an unpaired electron. If this enters the magnetic field, it aligns itself either in the direction of the North Pole or in the direction of the South Pole. The most important thing is the alignment before entering the magnetic field. If the alignment is previously directed towards the North Pole, the spin is in most cases completely aligned to the North Pole. In this case, this unpaired electron experiences an upward force. It can thus be shown that the spin of the electron has a magnetic moment and is either attracted by the North Pole, as in this example, and repelled by the South Pole and deflected upwards, or, as in the second example, exactly in the opposite direction.